For the second topic, I will show you the different methods or possibilities that we can use to compute the efficiency map of the electrical motor using FluxMotor or Flux, the emission toolbox. A small introduction about this topic. The first one is about the efficiency map and the comparison between the different method. Here we speak about FluxMotor and emission toolbox for this both cases, standard and the fast mode. What we mean by the efficiency map, as you can see from this picture, there is the curve torque as function of the speed for different possibility for the control. You have two modes of the control, MTPA or MTPV, max torque per voltage or max torque per ampere. There is also all the working point or the efficiency of the working point are located in this envelope. Generally, this map is characterized by 2 points. The first one is the base point, the point in which we have the maximum torque and also the maximum current and the voltage. The second characteristic is the maximum speed point. In this point, we have the maximum speed reached by the motor, and also we can see the different behavior of this of the motor in this point. Yeah, for the next slide, just a small comparison between the two methods that we can use to compute the efficiency map in Flux. The Flux 2D or Flux 3D. There is another possibility also that we can use Flux 3D to compute this efficiency map. For the fast mode, we can see that we use a main-to-static application to do the different simulation according to the variation of the current in D and Q axis. And this is a parametric solving scenario. This means that the variation of this current in D and Q axis will be automatized in the solving scenario. And from this, we can create a lookup table that we can use also this results or this lookup table. We will use it to compute the flux in DQ axis and the inductance in D and Q axis according to the Park model. The more advantage of the fast mode is that this workflow is really faster, and there is some drawback that we don't consider or the iron losses in the motor. I mean by this the rotor, stator, and the rotor. Also, we don't consider the position of the rotor. For the accurate mode, as you can see here, the difference is that we use a transient application. We use also always the same, the variation of the current in D and Q axis. And also in this case, we consider the variation of the rotor position. We use also the Flux in accurate mode. We use the sensors to compute the value of the efficiency. And also we consider both mode of the control, MTPA and MTPV. It depends if you are in the maximum power or the maximum torque. So there's some advantage and some drawback of this mode or this accurate mode. The first one is that it is slower because we have a transient application. We consider also the rotor position and we compute the iron losses, but we get an accurate results. In the third slide, I will show you just this. In this third slide, the method also used to compute the efficiency map in the case of FluxMotor. When you open FluxMotor, you go to the motor catalog, you open your motor, you go to the performance mapping. From this, there is a possibility to compute the efficiency map of the motor. This is the input that we have in this case. As you can see from this. When we put when we use this data and we run the computation, we use also the same behind. We use Flux and with a main-to-static application. This means that we don't consider the rotor position, and there is the variation of the current in D and Q axis. From this raw data, we use a park model to do the computation of the torque, the analytical formula. This means that we consider only the first harmonic, and from this we build the efficiency map. We consider also both command, the MTPA and the MTPV control. This is just a small introduction. I will show you directly from. I prepared an example here. This is a FluxMotor. I go to the test, performance mapping, sine wave. This is the different input that we can use to run the efficiency map. The first one, as you can see here, this is the thermal. There is a possibility to consider a temperature in different parts of your motor, winding and magnet. The same thing also if there is a cooling temperature. For the electronics and mechanics also, for the mechanics, this means that you will consider the mechanical losses according to the analytical model. This is the initial input. You have the current, the maximum line current or the current density for your motor. You have the max line voltage. You put the RMS value. You have the possibility to choose the mode, the command or the system control that you can use MTPA or MTPV, and also the maximum speed. There is some additional advanced input, if I can say this. This is also there is a possibility to consider a duty cycle. For additional input, you have the value or the number of computation of the current in D and Q axis. By default, we use 5. This gives us it is compromise. This gives us an accurate results, but the user have the possibility to increase this, modify or increase this number of computation in D and Q axis. But when we increase it, this leads to increase the time computation. The same thing also you have here. You can see the number computation for speed, and also the number computation for torque. It will be the same principle. For the rotor initial position, by default it is automatic. This means that FluxMotor will define automatically the initial position of your rotor. But if you select another mode, in this case, the user should put by himself the initial position of the rotor. The second point or the other point is match order. By default, in this case, we use a second order match, and the last point is air gap match coefficient. This allows to refine or control the quality of the match in the air gap. And this is about the advanced input. I will show you some results that we can get from Flux. Once this is done, you run your simulation. You can click here and you see the different maps that you can get. This is the efficiency map. As you can see here, you can see the variation of your efficiency in different working points. There is a possibility to save results, and if you want, for example, to change the inputs, for example, the current or the voltage, you run again and see both results. Export the results also as Excel or TXT file. This is about the possibilities of the efficiency map computation using FluxMotor. From Flux, as I said in the beginning, there is a possibility to do it in 2D and in 3D. You can see here from Flux Supervisor, you can open eMachine Toolbox, and you will get this window. As you can see here, in this case, I prepared a model, but you prepare your model from this one, and you run directly. This is the different inputs or the parameters of your model. You have the maximum phase current. You have the maximum phase voltage. As you can see also from this point, you have also the control system. There are different types. You have MTPA, MTPV. This is the accurate mode. This means that we consider the iron losses in stator and the rotor and the magnet losses. For the fast, we don't consider the iron losses on the rotor for both MTPA or MTPV. This is also another factor is X factor. This factor allows to adjust the iron losses to the measurement. This factor will affect the maps for iron losses, rotor losses, stator losses, and also the total losses. This means that if you have some depth that you don't meet the measurement, there is a possibility to adjust your losses by changing the value of this X factor. The other point here is the torque computation mode. As you can see here, there is two. You have electromagnetic torque and useful torque. The difference between both, in one case, we consider for electromagnetic torque, we don't consider the iron losses when we do the computation of the torque. For the second point, the useful torque, in this case, we'll consider the iron losses when we compute the torque. This is the maximum speed, is the speed that your motor can reach. The same principle also for the rotor initial position. It is automatic. This means that we do it automatically. If you use user, in this case, you should put the user put the value of the rotor initial position. You have also, as you can see here, you have also the same number of components for the current in D, the same parameters, I mean, for the current in D and Q axis, for the speed, and also the number of the components for one electrical period. These values, by default, Flux proposes some values. The user have the possibility to modify, increase or decrease these values. This can affect the time computation. By the default value that we have, we give us a compromise between the accuracy of the results and the time computation. About the numerical memory, as you can see here, the user can also select directly a dynamic, when you put 0 here, the user select directly a dynamic memory. This means that Flux will allocate the required memory to solve the project. There is also the possibility to consider the distribution during the computation. Just here, I will show you some results. The efficiency, there is the efficiency map. You have also, as I said before, the possibility to separate the different iron losses, stator, rotor iron losses, and the stator iron losses. And you have also the rotor AD current losses. And the same principle here also, you have the possibility to export or to archive the run to the, if you want to do the PBS run. And also you can select, export a result as a PDF or HTML or TXT file. There is a possibility to see directly the results from the folder where you have saved the project. You go to this folder and you can see the results as a CSV file. Yeah, this is what I want to show you about the possibilities to compute the efficiency map using Flux or FluxMotor.